Class, welcome back to the lectures on quantum field theory, and this is the second lecture for this chapter. We're again on introduction to group theory, and together with this lecture you can read along the books of Michio Kaku, Quantum Field Theory, F. Mandel and G. Shaw, Quantum Field Theory also, and of F. Gross, with title of Relativistic Quantum Mechanics and Field Theory. So this lecture starts with unitary groups, which are very important in particle physics. So the preservation of the lengths of vectors by orthogonal transformation is very important in establishing a correspondence between the unitary transformation SU2 and rotations in 3 dimensions represented by SU3. Unitary operators preserve inner products, which means that a unitary transformation leaves the probabilities for different transitions among the states unaffected. Under a unitary transformation, quantum mechanics is invariant. So unitary groups play a very special role in quantum field theory. When the physical predictions of a theory are invariant under the actions of some groups, that group can be represented by a unitary operator U. And also, unitary operators commute with the Hamiltonian. So you have this here. By the way, the unitary group UN consists of all n by n unitary matrices. So there is a special unitary group, and this is a subgroup of UN. And these are all the n by n unitary matrices with positive unit determinant that is equal to 1. The dimensions of SUN and hence the number of generators is given by n square minus 1. And so for SU2 there are 3 generators, and for SU3 you have 8 generators. And by the way, you will know later on, SU2 has 3 generators, and this represents the 3 gauge particles of the electroweak theory, and the 8 generators of SU3 represents the 8 gauge particles of the strong interaction, and these are just the gluons. The rank of SUN is n minus 1. So for SU2 you have 1 as its rank, and for SU3 you have 2. The rank gives the number of operators in the algebra that can be simultaneously diagonalized. So these operators are represented by matrices. The simplest unitary group is the group U1, and this is composed of 1 by 1 matrices or complex numbers written in polar representation. So you have here this one. And U1 is an abelian, since you can commute the representations in 2 different representations when you get the product. Many Lagrangians in the field theory are invariant under U1 transformation. So if you treat the problem in the complex plane, the invariance is really obvious. So if you have arbitrary complex number Z, which you can write in this form, r times the exponential I alpha. So when multiplied by e to the I theta, this gives just this one. You still have the same length, but your alpha is increased. So this just means that something is just rotated with the same length r. However, the angle is now changed, and in this case you have an increase in angle by theta. As a simple example, the Lagrangian for a complex scalar field here, sorry for that, but it's actually Lagrangian is written with a special L. So this is invariant under the transformation, this one here. So when you have this one, your exponential will just cancel and also this one here. So the Lagrangian is invariant under that transformation, under the U1 transformation. So when the Lagrangian is invariant under a transformation, there is symmetry. And in this case, your symmetry is the U1 symmetry. So force mediating particles called gauge bosons are associated with unitary symmetries, like U1 symmetry. And in electrodynamics, the gauge boson associated with the U1 symmetry is the photon. And later on in other theory, like this one is for quantum electrodynamics. For electroweak theory, your gauge boson would be W plus W minus and Z. And for the SU3 symmetry, that would have to be the 8 gluons. A U1 symmetry also manifests itself in terms of the conservation of various quantum numbers. And if there is a U1 symmetry associated with a quantum number A, then your U would have to be written in this form for the U1 symmetry. The importance of the U1 symmetry is that the Hamiltonian H is invariant under the transformation here. By the way, this is supposedly positive. That is supposedly positive, because that is the Hermitian conjugate of this one, is a Hermitian conjugate of this one. So that's the I there is supposed to be positive. So the adjoint U is also the inverse in this case. So you will have an identity if you multiply U and its adjoint. And these symmetries are present in quantum field theory with conservation of lepton and baryon numbers. So later on we will know these things. An element of the group U1 is a complex number of unit length. So U would have to be written in this form, where theta is a real number. And of course, if you go back to your mathematics in calculus, you will just remember that this is just a unit circle, a circle with radius 1 in the xy plane. The next non-trivial unitary group is the group U2, which is the set of all 2 by 2 unitary matrices. And being unitary, these matrices satisfy again the identity. If you multiply U and its adjoint, or it's the adjoint U times U is just the identity. For physics, there is a subgroup of U2 which is called special unitary group, and this is just the set of all 2 by 2 matrices with determinant 1, and this one is SU2, special unitary group, which are of course 2 by 2 matrices. And the generators of SU2, you have 2 square minus 1, that's 3. So there are 3 generators, and these are just the Pauli matrices which you have derived in your quantum mechanics. We will not derive the Pauli matrices here, but you can do so if you review your quantum mechanics. So you have this one, and this one. There are famous results in quantum mechanics, and these are when you study about spin 1/2 particles. So the rank of SU2 is 1, and there is one diagonalized operator, that is sigma 3 here. So again, familiarize yourselves with the Pauli matrices. 0, 1, 1, 0, 0i, negative I, 0, 1, 0, 0, negative 1. So are these Hermitian? This one is Hermitian. This one is Hermitian, and this one, however, is not Hermitian. Oh, I'm sorry for that. They're all Hermitian. So as we have said earlier, the rank of SU2 is 1, so there must be one diagonalized operator, as you have seen, sigma 3 in the basis that we've chosen. The generators of SU2 are actually taken to be 1/2 sigma I, and the Lie algebra is the familiar commutation relation that are satisfied by the Pauli matrices, and this is just this one. So we will just assume that there's a 1/2 there, but we will explain that later on why there is 1/2. Actually, it's because of the angle, because you have SU2 and SO3 being similar in structure, and later on we will explain that. So anyway, this holds true if you're just talking about SU2. Well, you have sigma I, sigma j equals I epsilon I j k sigma k. That is enough for SU2. But if you're now talking about the SO3 coming into the picture, you have to have this commutation relation. But anyway, they're just equal. If you cancel 1/2, that's just the same as this one. Since the Pauli matrices do not commute, SU2 is non-abelian. Okay, by the way, let's go back. There's supposed to be a factor 2. There's supposed to be a factor 2 here. If you... Sorry for that. So anyway, let's proceed. Recalling that the rank of SU2 is 1, there is, as I have said, one diagonal generator, and that is sigma 3. So an element in SU2 can be written as this one, of this form. Where the sigma j is one of the Pauli matrices, and alpha j is just a number. By the way, if you can't see that, it's just it is sigma j alpha j, not sigma j sigma j sigma j. So here to understand the presence of the factor 1/2, explore the correspondence between SU2 and SO3, since both SO3 and SU2 preserve the lengths of the vectors. So if we look at this vector R, xi, yj, and zk, and we construct the matrix of the form sigma R, then we would have this one. So that is your sigma x multiplied to x, sigma y multiplied to y, and sigma z multiplied to z, and it will give you this matrix here. This is your sigma dot R, and the determinant of this matrix is the length of the vector. And the trace of the matrix here is 0, so you can cancel, the elements of the diagonal is 0, and of course the matrix is Hermitian. Now consider a unitary transformation of this matrix. So for example, we take this transformation, and we choose you as your sigma x, and this one is just your sigma dot R here. So if you do the operation, you will be able to get this matrix, and this matrix is traceless and is also Hermitian, and moreover the determinant is preserved, and it again gives the length of the vector here. So just like SO3, SU2 preserves the length of the vector. So the structure of SO3 and SU2 are really similar. The correspondence works by considering an SU2 transformation on a two-component spinor like this one. This one is a spinor, which you've learned that term in quantum mechanics, where x here is given by that expression, and y is given by this expression, and of course z is given by this expression. So the SU2 transformation on psi alpha beta is equivalent to an So3 transformation on a vector with 3 components. And what makes it special is that in this equivalence, an SU2 transformation has 3 real parameters that corresponds to the 3 angles of an SU3 transformation. So for SU2, we label the angles as alpha, beta, and gamma. So this is the most important one. Half the rotation angle generated by SU2 corresponds to the rotation generated by SO3. And that is the origin of 1/2. For arbitrary angle alpha, a transformation generating a rotation about x in SU2 is given by this matrix. And this transformation corresponds to the rotation in equation 3.10, a rotation above the x-axis, and that is just (1,0,0) cosine theta negative sine theta 0 sine theta cosine theta. So that is the equivalent in SO3. And the unitary operator for SU2 transformation generating a rotation around the y-axis is just this matrix, and of course the angle there is beta, and this corresponds to the transformation in SO3 as well. You can review the lecture, the first part of this lecture in chapter 3 to get the RY and get the expression for RY. And finally, for a rotation about the z-axis, the SU2 transformation is just equal to this matrix. So all 2x2 matrices are specified by 2 parameters, complex numbers A and B, where your U is just of the form A negative B star or B conjugate and B A star, where for an element of SU2 the determinant is positive 1, which requires A square plus B square to be equal to 1. Later on, we will do some Lagrangians that are invariant under SU2 symmetry, and this is of course very important in electroweak interactions, and we'll be able to make a correspondence to this to correspondence of the generators to the particles W plus, W minus, or Z boson that carry the weak interactions. So for SU3, this will be very important in the interaction of quarks, and of course quark interactions, they exchange gluons, and there are 8 gluons comprising the quantum chromodynamics, theory of quantum chromodynamics. So SU3 has 8 generators, and these are called the Gilman matrices. So let me just show you what are these matrices. And again, the rank of SU3 is 2, so therefore you can find 2 matrices here that are diagonal, and these are just the 2 matrices that are diagonal and or diagonalized matrices, and these 2 matrices are actually representing colorless gluons. And if you notice, all the 8 matrices here, all the 8 generators are traceless, and they satisfy the commutation rule, which is just this one here. And your Fijk is just given by this constants. So in this case, you have, if you repeat the indices, that will just give you 0. So all others except these are 0. So if you also, if you have F 1, 2, 3, this is equal to 1, this is also equal to F 2, 3, 1 is equal to F 3, 1, 2. But for non-cyclic, this is cyclic permutation of 1, 2, 3. But for non-cyclic, you will have negative. So F 1, 3, 2 would be negative 1, and this is just equal to F 3, 2, 1, F equals 2, 1, 3. So that's the algebra for SU3. If you explore later on, as we will go later on in this chapter, hopefully we can reach that. If you reach the quantum chromodynamics, we'll be able to see how this works. So we'll now go to Casimir operator. This is a nonlinear function of the generators of a group that commutes with all the generators. And of the number of Casimir operators for a group is given by the rank of the group. So for example, SU2 would have 1 Casimir operator, and SU3 would have 2 Casimir operators. So for SU3, the generators are the angular momentum operators, and in this case you will have this. A Casimir operator is an invariant, and in this case the invariant suggests that J square is a multiple of the group identity element. So as a summary, group theory places an important structure in particle physics, because groups are used to describe symmetries. The structure of the group is defined by the algebra among its generators, If two groups have the same algebra, they are isomorphic or they're related. Unitary transformations preserve the probabilities of state transition in quantum theory, and as a result, the most important groups in quantum field theory are the unitary groups U1, SU2, and SU3. And all of the standard model is actually the group which is a product of U1. This is the standard model, and if you do advanced course in particle physics or in particle physics, not really advanced, but even in introductory particle physics, you'll know that standard model is the group which is the product of these three groups. So this is for QED. This one is for the electroweak theory, and this one is for QCD. So as you can see here, there's well, as an examination, but we'll not do an examination for this course here. So anyway, that's it for this session or quantum field theory, and I hope you got something out of this lecture.